Hi students, welcome to the next lecture series of basic electrical engineering. So this is the second video on DC generators. In the last video we have seen the basic principles what are present behind the working principle of DC generator or DC machine. So and in the last class we have seen that there are two types of EMFs will be there, that is a dynamically induced EMF. One is, what is that? Dynamically EMF, and second one is statically induced EMF. So we have seen, so statically induced EMF is in the case of the transformer, okay, and dynamically induced EMF in the case of the rotating machine. So this we have seen in the last video. So for dynamically induced EMF, what we require? So we require a field, okay, so we require a field, then the conductors will be required. After that we require, so there is a cutting action should be there. So the cutting action should be there between this magnetic field and the conductors, then you are getting the dynamically induced EMF. So if you observe, so let us take this principle you have seen in the lower classes. Let us take the flux lines are having the flux density B like this. So B is the, so we are taking the flux density, here we are taking the flux density, B is the flux density. Next, so the conductors, okay, the conductor is having active length, okay, the conductor length is, active length means from this to here only, the length of the conductor is LC, that is active length of the conductor, okay, so active length of conductor. Next is, so this is the length, we are taking it as LC, and this conductor is moving with the velocity of, that is, it is rotating, so it is rotating with the velocity of V, it is rotating with V. So V is the linear velocity, it is not the angular velocity, you remember that. So V is the linear velocity, with the linear velocity it is rotating this conductor. So whenever it is rotating, so it is making some angle, this is the field, okay, this is the flux B, and it is making some other angles. So with linear velocity V, it is rotating, so making an angle theta between them. So that is the theta is the angle between B and V, okay, theta is the angle between V and D. So from this we can write it as the dynamically induced EMF, we can write it as, it is proportional to the product of, that is a cross product of V into B, okay. So the dynamically induced EMF, to remove the proportionality we can write it as, you know already, BLCV sin theta, okay. So theta is the angle between them, so we are taking the theta is the angle between. So whenever you have the conductor is a linear conductor, if it is like this it is no problem. Whenever you have the conductor is some different shape, if you consider, so if you have the flux density lines will be like this, this is the conductor. So if you have like this, what you have to do, so we can find the, so dynamically induced EMF, so with the differential values, so you can find it as BV sin theta, we can find for some length, considering some length of the conductor we will calculate first. So let us consider this is the DL length we are consider. Then so if you take integration on both sides, what you will get, dynamically induced EMF will be integration of BV sin theta DL. So integration of sin theta DL we will get. So we can make it as, so we can make the integration for the length L. So then we will get it as BV. So BV sin theta DL, this is the, so if you write like this, you can write as finally length B into cross product of B into V, also we can write for the length of DL. So this can be, this is the dynamically induced EMF when you consider the conductor in different shape. Let us see, so whenever you have, so I already told, so the direction of induced EMF, so EMF direction can be found by using, so what is that, Fleming's right hand rule. So we already discussed about this. So Fleming's right hand rule we are going to use for the direction find, okay, Fleming's right hand rule. So in the Fleming's right hand rule, so forefinger is indicating, so what is the forefinger is indicating, the flux lines, it is indicating the flux lines. Then so thumb is indicating, we are already know thumb is indicating the linear velocity, okay, so the linear velocity on the conductor, that is in which direction it is rotating. Next is middle finger is indicating the EMF produced in the conductor. So EMF produced in the conductor you can find by using the middle finger. So this is the Fleming's left hand rule we are going to use for finding the direction of induced EMF in the conductors mainly. Let us see how what is the EMF will be induced in the conductor, in which shape the EMF will be induced in the conductor. If you observe, the EMF will be induced in the conductor. Let us see here, let us consider the north pole and the south pole here. Let us consider the north pole and south pole. Always we are already know the north from the flux lines will always travels from north pole to south pole. Let us place the conductors. So like this I am placing the conductors. So whenever it is, consider the conductors are placed like this here, okay. So here, so the conductors which are present under the north pole we are taking, okay, the cross direction. Here it is a dot, and it is a, once again we are taking it as a 1 2 direction, 1 2 3 and 4 conductors. So if you observe the conductors, we found that the current going here you can apply. So what you can apply? Fleming's right hand rule you can apply, so to find the direction of induced EMF, okay. Fleming's right hand rule you can apply to find the direction of induced EMF in this conductor. So whenever it is rotating like this, so you can apply, so it is rotating in the linear velocity v and the flux lines will be like this b. So that means it is having the at position 1 if you observe that position 1 the flux lines will be like this and the linear velocity is also, so flux lines will be like this. Let us consider the linear velocity will be in this direction. So they both are opposed. So what is the dynamically induced EMF in this case? That is at position 1 it will become 0 because the theta angle is between them is 0. Next, when you observe in the second position, V will be like this and B is like this. So at the second position you have the theta will be 90 degrees. So EMF dynamically induced EMF will be of a maximum value at this condition at position 2. So let us consider at position 3, once again the flux lines are traveling like this. So and the velocity will be like this. So velocity of the linear velocity on the conductors will be in this direction only. So that here also you can get dynamically induced EMF will become 0. And once again if you observe in the fourth position, so the flux lines will be like this and the linear velocity will be like this. So it is having 90 degrees between them. So dynamically induced EMF will be once again maximum, but it is a negative maximum which is reversed. So if you draw the waveform, at different positions, if you draw the waveform of induced EMF at different positions, we can observe like this. So you have the positions will be like this. So at first position once again 0, at second position, okay, this you can consider it as a second position, it will become, so second position it will becoming the maximum value, and at the third position, this is the third position, it is becoming the 0 once again, and the fourth position it's again becoming the negative maximum. So induced EMF we can draw it as, that is a dynamically induced EMF. So with respect to theta if you draw, so the induced EMF will be like this, which is of fifth position if you consider, once again the same position of 1 and 5, so that will become 0. So induced EMF will be always a sinusoidal, but we are studying about a DC generator, but we are getting the here alternating EMF. So how to change this alternating EMF to unidirectional EMF or DC induced EMF? That is the next point here. So for this we will consider elementary DC generator. Let us consider a elementary DC generator here. So if you observe elementary DC generator, so in the elementary DC generator, just I am drawing a north pole and here the south pole like this, okay. So let us consider the conductor positions will be like this, okay. So I am not perfect in the drawing, okay, please adjust and understand, okay. So this is the some brushes we are considering, that is the slip rings will be connected here like this here. So this is of a load is connected for this. Next is you have another slip ring here, So you have another slip ring and we are connecting the brush. I will show the diagram clearly later. So here this is the diagram. So whenever it is connected, so this is the, so I will indicate with another sketch. So this is S1 and this is the B1 and this is the B2, this is the S2. So S1 and S2 are slip rings and the flux lines will be traveling from, always we are already know, from north pole to south pole it is traveling. So when it is traveling, let us consider the length of the conductors. Here it is A and B and this side it is C and D. Let us consider the length of the conductor and this is the plane. Okay. So if you observe here, so whenever you have the dynamically induced EMF, so if you see the front view, let us draw the front view. If you observe the front view like this, if you observe the front view, so and in this front view we have positions, different positions will be there. Here this is the first position, okay, this is the second position and this is the third position and this is the fourth position, this is the first position. So we have, whenever it is rotating at first position and second position, we are already know, so it is always, so there is a linear velocity and flux lines is making some other angle, so that you are getting dynamically induced EMF will be a maximum value and it will becoming 0. So for that what we have to do, you are getting a alternating EMF we have to make. So you are getting, so let us draw the EMF, how you are getting the dynamically induced EMF, like this you are getting. So our target is to convert this dynamically induced EMF into here. So this can be converted like this, so which you are making it as, try to making it as a unidirectional. Okay, so we are trying to make that by using the, so the commutator. Okay, so this can be done, this function can be done by a commutator. We will discuss later what is the meaning of the commutator. So whenever you have this like this, you have to use the commutator. So whenever the conductor positions, so when under the, so we are already know, always under the north pole. So let us consider under the north pole the current is going into the plane and the under the south pole the current is coming out like this. So the current is coming out here, the current is entering here, so that the current is going to through, so what it is going from, so it is going from like this and from this point to this point like this. So and it is going like this. So we can consider, so let us consider the point M to L. After some period of time, this conductor AB will comes under the influence of south pole because it is rotating. So AB will comes under the influence of south pole and CD will comes under the influence of north pole. That means, so what we are expecting, CD is under the influence of north pole. So CD will be means, that means the brush 2 is taking now. So from the brush 2 the current is traveling. Now I am indicating in the opposite direction, because whenever you are rotating, so the brush 2, from brush 2 it is going, because AB will comes under, see, understand here. So here AB will comes under, AB length will comes under the influence of south pole and this CD length will comes under the influence of north pole. So that because always the current will enter, so that means the current is taken from the, in this case B2, and the current is traveling from L to M. Previously it was traveled from M to L, now it is traveling from L to M. That means it is reverse, it is going, that is why you are getting this waveform. So what we have to do to convert this waveform into unidirectional, we are going to use, even though you are using the different slip rings and the different brushes, so you are getting the like this. So that what we are doing is, we are going to connect a commutator. Okay, so let us understand how the commutator, this is also one of the important question. So commutator we are using, so what is the function of the commutator? So commutator is such a device which will converts. Okay, so it is converts, so you are getting AC to DC. So it can be defined as a mechanical rectifier. In the case of the DC generator, it is defined as the mechanical rectifier. Rectifier you already know, rectifier means which is converting AC to DC. So mechanical means it is having some mechanical construction. So if you see the construction of the commutator, so the commutator is a structure of a cylindrical structure, so like this. So it is a cylindrical structure, and this cylindrical structure was divided by a insulating material. So this structure was divided by insulating material, okay, like this. So this is on this side we have one brush is connected, okay, on this side we have another brush is connected here. So brushes are connected, that means the brushes are attached with this, so the brushes will not move, and this commutator is so separated by which material means, so normally it is separated by a mica insulation, it is separated by mica insulation material. Next is, and it is made up of hard drawn copper, it is made up of hard drawn copper, because it can be withstand the whatever maybe the damages or sparks, it can withstand with respect to the copper. So that's why it is made up of the hard drawn copper. So whenever you are connected this, the commutator, so what is happening is, so because of that, so what will happen, let us see. So if the commutator segments, let us consider the commutator segment, this as A and this is B. So whenever you connect it like this, so because this A and B in the first position, one is in contact with another one, so the current is going into and it is coming taken, but with this the brushes are taken. So like this the connection will be connected here. So here the current will be connected like this, so the load will be connected like this. Let us consider. So here, so the length will be here AB length and here will be CD length. This is the first case. This is the first case. So whenever you change the same thing, so let us consider after 90 degrees rotation. After 90 degrees rotation, so what will happen? That means, so the AB will comes under the influence of south pole. Let us draw once again the commutator segment. So if you see the commutator segments, the commutator segment position also will be changes. The B will comes here, A will comes here, but if you observe here the conductors will be, so the conductor is, it is like this. So let us see what is what is happening here. So CD will comes here and AB will comes here, okay. So that means here once again the current is going like this and the current is coming like this. So let us see the direction in the both cases to the external load here. Load I have placed here. So for the external load you observe how it is going. So if you observe the load direction, you can observe here both and here and here. So you see here, so the current is going into means the current is coming going brush B2 and this is the brush B1. So it is going brush B1 and point M. Let us consider this is the point M and here to L, and it is going like this and the brushes. And if you observe here also it is going like this. So here you have the brushes, I forgot, sorry. So here also you have the brushes. These brush positions are fixed here, that is B2 and B1. So B2 and B1 as the current is going like this once again M to L. That is the we are making with respect to by using the commutator. This is the function of the commutator. I think so you understand the what is the function of the commutator. So because of this, what you are going to get, the output you are going to get, it is a pulsating DC waveform. Pulsating DC waveform we can get because of this commutator segment, but we don't require this pulsating DC waveform. So we require a purely DC waveform. So purely DC waveform means, so normally the DC will be like this. So we are representing with this like this. So we are getting the waveform will be like this. So we are trying to make, so this pulsating DC also we are trying to convert this pulsating DC into like this. So how we are going to convert is by using some techniques. So one of the technique is by using more number of conductors. Let us see how we are converting. So this is the your commutator, sorry, your armature you can take. So this is under the north pole, okay, this is under the south pole. So you have the conductors. Let us consider the 4 conductors are there here, and so you have the 4 conductors I have connected A, and this is the B, and this is the length C, and this is connected to D like this. Let us consider. So 4 conductors means totally how much angle will be there here? Total how much angle? 360 degrees. 360 degrees you have the 4 conductors, that means you are going to get 90 degrees. So for each 90 degrees only, for each 90 degrees, so what we can take? for each 90 degrees we can take the, so 90 degrees the brush is in contact, brush contact will be there, brush contact will be there only for how many degrees? It is 90 degrees. So here you have the 4 conductors. So before the D you are getting the A, okay, like this if it is rotating. So after A you are getting B, and B to C and C to D, like this. So if you draw the waveform of different EMFs, so let us consider, so if you draw the different waveform, so let us consider A as a reference. So this is the A waveform. Next, before, after 90 degrees, is it right? After 90 degrees, because it is contact with this B, so you are getting the B waveform will be like this. So this is of B, okay. So next, after 180 degrees, after 180 degrees you are going to get the C will be a starting here, C will be starting here, that is a C waveform, C waveform only starting here. Next, after, before the 90 degrees only it is going to start, or you can say it as after how much angle? After 360 degrees we can say it is going to start. So I can consider before 90 degrees, just I am considering the waveform of the D waveform. So D waveform will be like this, before the it is starting, like this. So if you observe all the waveforms, this is of D and this is with the C, this is of A. So if you observe, because the brush is in contact only 90 degrees, so it is flat tapped wave only you are going to get. So the waveform will be like this only. So if you observe the output waveform, so if you observe the output waveform, the output waveform will be, you can observe like this. So this is of induced EMF. So if the more conductors, let us imagine if more conductors are connected like this, what will happen? So you are going to get more flat current, sorry, more flat induced EMF you are going to get approximately. In the case of this, you are going to get dynamically induced EMF is more what we can say, so more constant you are going to get because of the more conductors we are using. Practically conditions we are using the more conductors, okay, right. Next, see, one more idea is also used here, one more idea here. What they are doing is, so instead of having, so here this is all called as the pole core, and we have the pole shoe here. So they are placing the pole shoe, the conductor will be, the armature will be like this, so that you are providing the more flux and you are making the angle. So the angle for this conductors, so you are making the, so this is of flux lines and this is of V. So the linear velocity and the flux density, we are making the angle at different instants, we are making it as a sin theta, that theta we are making it as a 90 degrees. We are trying to make this theta value will be a 90 degrees at a different instance, because this conductor is rotating or this armature is rotating. So we are making the theta will be 90 degrees, so that the flux wave, so that the flux wave will be like this. So the single wave means like this you are going to get a single wave. So like this what we are going to get, so many number of conductors means like this you are going to get, like this you are going to get. So because depending upon the angle, so you are going to get the, depending upon the angle you are going to get a pure DC waveform you can observe in the case of this, in the dynamically induced EMF, whenever you are making the theta angle will be converted to 90 degrees. So you are getting a pure DC waveform by using this a pole core. I will explain what is the meaning of the pole core, and this is called as the pole shoe when we are discuss the constructional detail. So that you are going to get a flat tapped wave, in the case of the here. So maximum we are going to get the flat tap, this is called as the flat tapped wave we are going to get. So now we got the purest form of the DC because by using the commutator, okay. So that's all for in this video. In the next video we will see the constructional details of DC generator, and the DC motor is also same. So if you are seeing this channel first time, please like, share and subscribe the channel to your friends also, which is very useful for your external exams. Thank you very much.